Welcome to section 12.5. This is the last section that we're doing in chapter 12, and this is kind of the big idea of what we call an integral, which is looking at areas. And so we're going to start talking about this second main idea in calculus, and we'll talk about this area under the curve. What you first want to know is these summation formulas, and we'll show you how to use them in class, but it's this idea that I'm taking the sum from 1 to a value of n of a number c, and that equals c times n. And we're going to show you how this works, but it's asking you to add up c n different times, so c plus c plus c plus c, and I can just do c times how many there are, and I get the same thing. Okay, the second thing, I'm asking you to add up from 1 to n, this value of I. So it's basically saying from 1 plus 2 plus 3 plus 4 plus 5 plus 6, all the way up until n. And they give you a shorthand for that, n times n plus 1 divided by 2. By the end of this, you'll be pretty good at these, but there are some of them that you will need to know. Third thing is we take the sum from 1 to n of I squared. So that means 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, blah, 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 all up to n squared can be found by taking n plus 1 times 2n plus 1, all divided by 6. And last one that we're going to look at is if we take the sum from 1 to n of I cubed. So again, 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way up to n cubed is the formula n squared times n plus 1 squared all over 4. And we're going to use these in some of the homework questions and the things that we do, but I just wanted to at least give them to you first. Okay, now we're going to do one problem for the whole lesson, and we're going to break it up into different parts. And so I'm going to start with the most basic of all ideas. I'm going to start with a curve x squared, and I know the points are 0, 0, 1, 1, 2, 4. And you'll notice they've kind of spread this out, and this seems like pretty big graph paper for this little curve, but I'm going to show you this general idea. What we would like you to do is approximate the area from the curve down to the x-axis. It's called the area under the curve between 0 and 2. Now, what I'm asking is, if I look at this and draw this line here, can I find this area underneath to the x-axis? Well, the problem is our geo skills don't give us a possibility of finding the area. It looks triangular, but this is curved. And so what we have to do is called a Riemann sum, and we're looking at this idea of adding up rectangles. Well, if I'm adding up a rectangle, I always use the height at the end that I'm working with. So the height at 2 times, and I'm basically going to carry that across. Okay, so if I look at the area of a rectangle, I know that the area is length times width. Well, if I look at the length, I'm going from 0 to 2, so it has a length of 2. The width or height maybe be better. At 2 squared, I get 4, so 2 times 4 is 8. So the area under the curve is 8 units squared. All right, so taking a look, again, we're looking at if we can approximate now. Now, looking at this approximation, let's be honest, we have seriously over-approximated this area underneath the curve here, because look at how much space. I mean, we've over doubled the amount of space. So by using one rectangle, our approximation is pretty bad. So here's what we're going to do. We're going to try this again, only instead of using one rectangle, let's try and use 4 rectangles. So let me slide this down. We're going to try 4. So I still want the same points. So I have 0, 0, 1, 1, 2, 4. So I've got this curve. And if I want 4 rectangles, basically I'm going to look at the width. And I'm going to walk you through the process because we're going to get more and more and more rectangles. I'm going to take the length of this, which is 2, and I'm going to divide it by the number of rectangles I want, which is 4. So 2 divided by 4. Each rectangle then is going to be 1/2 or 0.5. And so at every half, I'm going to kind of make a mark because this is going to be my indicator for what I'm doing. Now, Whenever you do these rectangles, we always want to use the right-hand side to make our rectangles. So what I do is I start at the right. I start at the farthest point, which is 2. And I go up to my graph, and I'm going to draw this line. And I'm going to take this over until I get half, and then that's when I'm going to draw my next one. Okay, so there's my one rectangle with length of 0.5. And then I'm going to go again at 1.5, and I'm going to go up and hit my graph, and I'm going to drag that line straight across until I get to 1, and then I'm going to bring it down. There's my next rectangle. Then I'm going to go to 1, and where it hits my graph, I'm going to start there, and I'm going to go over until I get to 0.5. There's my third rectangle, and then again, I'm going to go to 0.5, and I'm going to go up, and I draw my rectangle. There's my fourth rectangle. Okay, now we know that each width is 0.5 because we set that up to be 4 rectangles. Okay, but the question is, what's our height? And the height of this fourth rectangle, and if you want to label them, whatever, I'm going to start with the big one. The height of this first rectangle comes from the value at 2. So the height here is the y value when I do 2. And the second rectangle, we get the height from when we put in 1.5 into our function and it touches our graph. So this is the value at 1.5. And then I go to my third rectangle, and in order to get the height, I use 1 in my function, and I find where it hits the graph. So it's f of 1. And the last one, to get my fourth rectangle, I use at 0.5, and I hit where my graph hits 0.5, so this is at f at 0.5. And I want you to kind of keep in mind, and I'm writing this specifically this way so that I can kind of show you as we go through. Okay, so how do you find the area? In order to find the area, we take the width times each height, and we kind of add them together. I'm going to use width and height because I think that's nicer. So if I do rectangle 1, my width is 0.5, and my height, if I put in 2, again, this function is y equals x squared, so if I put in 2, 2 squared is 4, so my height is 4. That's my first rectangle. I do it again for my second rectangle. My width is 0.5, and to get this height, I put in 1.5, and 1.5 squared is 2.25. Okay, I do it again, 0.5, that's rectangle 2. Rectangle 3 is I do 0.5 times the height at 1. Well, if I put in 1, 1 squared is 1, plus my last one, 0.5. I'm running out of room here, but I put in 0.5, and 0.5 squared is 0.25. Now, what I'm going to do is try and help us simplify this along the way. If you notice, they each have this 0.5 in common, so I can take this width, and I can basically look at it as the sum of the heights. So I can take the width, and I'm going to write this in, the width, and then multiply it by the sum of my heights. So either way, it doesn't matter if you do it this way because there are only 4, or you do it kind of differently. Either way, you get 3.75 units squared. Now, I don't know about you, but this is a way better approximation because look at my overage is way less. Now, I still have some overage, so there's a little bit of a need for a better approximation, but it's this idea that when I run through, I'm looking for more and more rectangles to help me kind of lighten the overage that I have. So let's try it again. If you flip to the back, we're going to do it one more time, only this time we're going to do 8 rectangles. So 0, 0, 1, 1, 2, 4. Okay, and again, I'm looking at y equals x squared. Now, let's talk about our width, and whatever you start, I want you to start with your width. I know the distance from 0 to 2 is 2, and I want 8 rectangles this time, so I'm going to divide it by 8. So each rectangle is 0.25, or 1/4. Okay, so what I'm going to do, like the last time, I'm going to start at the end. And if I notice, this I can split into 8 rectangles. And basically, we've set this up really nice for you that you can do it at every line. So I'm going to start at 2 because I think it's always best to start at the back. And I'm going to go up till I hit my graph. And I'm going to go over to the next line, and there's my first rectangle. And I'm going to use this next point, which is 1.75. And I'm going to go up where that hits my graph. And I'm going to move that straight over and come back down. Okay, this is at 1.5. So my next rectangle, so here's rectangle 1, 2, and I think it's going to help to label it. At 1.5, I go up to where it hits my graph, and then I go over to the next line and bring it down. That's going to be rectangle 3. The next value is at 1.25, so I go to where it hits my graph, and I go over to the next line. And at 1, I go to where it hits my graph, and I go over to the next line. So this is rectangle 4 and rectangle 5. At 0.75, I go to where it hits my graph and I go over. That's rectangle number 6. That brings me to 0.5. So I go over and down. That's 7. At 0.25, I do my final rectangle, and that's rectangle number 8. And so as you look, again, I'm trying to show you the process, and I'm trying to walk you through as easy as I can. But here's the idea. You start at the back side, and you work your way forward. Now, not always are they going to be this nice, kind of keep in mind, but I'm trying to show you where the y values kind of come into place from the x values. Okay, so let's do it again. In order to find the area, we can take each width and multiply it by its height, or we can do each width, the width times the sum of our heights. And I'm going to take you this way because I think it's going to help eliminate some stuff at the end. Okay, so here we go. My first width, each of these have a width of 0.25. And what I'm going to do is I'm going to take the value at 2, which is my first height, plus the value at 1.75, which is my second height, plus the value at 1.5, which is my third height, the value at 1.25, which is my fourth height, and you can keep going, right? The value at 1, which is my fifth height, plus the value at 0.75, which is my sixth height, plus the value at 0.5, which is my seventh height, plus the value at 0.25, which is my eighth height. And personally, this is the way that I kind of set it up to make sure I'm set. And again, you're going at increments. If this was like going by 0.5s, I'd go to 0.5 and then another 0.5 and another 0.5. It just depends on your increments. Okay, now you can put these kind of in your calculator, and that's what I would do personally, is go to my table or hit trace and just plug these values in. But I have 0.25 times f at 2 is 4, plus f at 1.75 is 3.0625. F at 1.5 is 2.25. F at 1.25 is 1.525. And you can keep going, right? All the way till you get f at 0.25, which is 0.0625. And so what I would do is, again, you keep going your whole way through. I would get this again from my trace menu in my calculator. But if you add all of these y values up and then you multiply it by 0.25, you end up getting an area of 3.1875 square units, or units squared, depending on how you write it. And so these are great approximations, but let's be honest. We are never going to get the exact area under a curve until we make as many rectangles as we possibly can, like infinitely many. And so what we're going to do is mix in 12.4, the limits to infinity, with the idea of area of rectangles. So I'm going to walk you through this last one. If we're trying to make an n rectangles, let's start with the width. And we said the width, let's see if I can actually make that clear as to what that says. We said the width is the value 2 divided by n, because we're going from 0 to 2. Okay? Now, if we take the area, and I'm going to try and walk through this as best as I can go through it in class as well. We said the area was the width times the sum of the heights. And so if I look at this, my width is 2 over n, and I'm going to put it in brackets, and then we look at the heights. The heights are first at 2 over n, plus my next height will be my next multiple of that, so 2 times 2 over n, plus it'll be the next multiple of that, so f times, 3 times 2 over n, plus as we keep going, we're going to keep going and going and going in increments of whatever this 2 over n is, and the problem is I don't know. And so here's what's going to happen, and this is where you got to kind of stick with me for a little bit as we follow this through. We're going to take the width, and instead of saying let's add all of these up, we're going to use our summation notation from 1 to n things, because we're going up all the way until we get to n increments of this 2 over n. Okay? So I have to use a different variable because I'm going from 1 to n. So the way I say this, f of I times 2 over n, where this is my width, basically this makes my width, and this is basically adding up all of the heights as increments as I'm putting them in. Okay, so what I need to do is look at what is my function. My function f, remember, f of x is x squared. So I'm going to take this idea and I'm going to square it. So 2 over n times the sum from 1 to n, and now this f of I times 2n, I'm going to square each of these, because I'm really asking what's I times 2 over n squared, and I'm plugging it in this function, f of x equals x squared. Okay, so let me show you what that looks like. 2 over n times the sum. When I square I get I squared. 2 squared is 4 over n squared. Now, what I'm going to do is I'm going to combine this and this together, and I'm allowed to do that. And so the way it works is if I take 2 times 4, I get 8. N times n squared is n cubed times the sum from 1 to n of I squared. Now, hopefully, as you're looking at this, you can think back to those summation notations that we had at the top. And so what this really means is I have 8 over n cubed. Now if I look at the formula for the sum of I squared, what you get is n times n plus 1 times 2n plus 1 all over 6. And so this is the formula to find the area of n rectangles for y equals x squared from 0 to 2. Okay? And this is the formula that we're working with that we just found for our function. Now, how would I find the exact area? Let me go back a second. This would say if I want to find for 42 rectangles, what I would do is make n equal to 42 and plug it in the formula. It would give me an area, which is great, but again, it's still an approximation. And if I want an exact area, I have to use infinitely many rectangles. So we go back to the end of 12.4 and we say, let's take the limit as n goes to positive or negative infinity for our function. 8 over n cubed, n plus 1, 2n plus 1, all over 6. Now, I'm not going to do all of the work because this work we did was in 12.4. If you feel like, hey, you need to go through it again, fine. Or if you want to divide out this n cubed, you could do that too. But we found 8/3. And so what we didn't tell you in section 12.4 is that you just found this exact area under a curve for x squared, and I'm looking at this parabola, from 0 to 2, you just found this area. Now, when you get to calculus, how does this translate? Well, that's great that you found this area. What they're going to ask you is to revolve this around the y-axis and create a bowl. And they're going to ask you, okay, if I can rotate this around, what is the volume that this bowl creates? And so we're doing a little bit of the background work to then be able to go to calculus next year and say, okay, let me find the volume of the shape that's created. And I know you're super excited as you think about this, but this is kind of the idea. We're going to be working more and more. Please, whatever you do, give this homework a shot before you come to class so that we can really dig into what is it asking, how am I supposed to make it work, things like that. Okay, so that's the end of 12.5. Thanks for watching.